Deep in the vastness of the universe, some stars live fast and die young. When their nuclear fuel runs out, they collapse under their own immense gravity, leaving behind objects so dense, so extreme, that a single teaspoon of their matter would weigh billions of tons, heavier than all the buildings, mountains, and oceans on Earth combined. These are neutron stars, cosmic remnants born from the violent deaths of massive stars. But here's the real mind-bending part. The visible surface, glowing brightly in X-rays and spinning at dizzying speeds, is just the beginning. Beneath it lies a world so alien, so extreme, that the laws of physics as we know them begin to break down. Pressures in the core are over 100 billion times stronger than anything we can produce on Earth. Temperatures reach millions of degrees, and matter is squeezed so tightly that protons and electrons merge to form neutrons. Scientists call this region the inner core, and it may hold states of matter that don't exist anywhere else in the universe. Could it be a sea of superfluid neutrons flowing without friction? Or perhaps a dense soup of exotic particles known as hyperons? Or even free quarks, the building blocks of protons and neutrons themselves? Some theories even suggest the core might contain strange matter, so stable that if it touched normal matter, it could convert it instantly. And yet we can't see it. We can't touch it. All we know comes from distant signals, the tiniest ripples in space-time called gravitational waves, and high-energy X-rays emitted from its surface. But each new observation hints at the unimaginable extremes hiding in the heart of a neutron star, a place where nature pushes the boundaries of reality itself. Today, we'll journey into this cosmic mystery, diving deeper than anyone has ever dared to uncover what might truly lie at the core of a neutron star. A place stranger than science fiction, a place where matter itself is transformed into something beyond comprehension. To truly understand what lies inside a neutron star, we first need to explore how it forms and why it is considered one of the most extreme objects in the universe. Neutron stars are born from massive stars, typically 8 to 20 times the mass of our Sun, that have exhausted all their nuclear fuel. A star shines because of nuclear fusion in its core, a process in which hydrogen atoms combine to form helium, releasing enormous amounts of energy that push outward and balance the star's inward gravitational pull. But when the fuel runs out, fusion stops, and gravity has nothing to resist it. The core collapses catastrophically, and the outer layers of the star are ejected into space in a supernova explosion. One of the most powerful events in the universe, briefly outshining entire galaxies and scattering heavy elements like iron, gold, and uranium across the cosmos. During this collapse, the core becomes so dense that electrons are forced to merge with protons, forming neutrons through a process called inverse beta decay, a reaction that transforms normal matter into neutron-rich matter. The result is a neutron star, an object made almost entirely of neutrons, where matter is packed so tightly that its density exceeds that of an atomic nucleus, roughly 4 times 10 to the power of 17 kilograms per cubic meter. To visualize this, imagine compressing the Sun into a sphere just 20 kilometers across, about the size of a small city. 1 teaspoon of neutron star material would weigh about 6 billion tons, the equivalent of Mount Everest compressed into a sugar cube. The gravitational pull at the surface is even more extreme, around 200 billion times stronger than Earth's gravity. A 70-kilogram person on Earth would weigh over 14 billion tons there. Gravity is so strong it bends light and warps space-time itself, creating a phenomenon called gravitational time dilation, where time moves slower near the surface compared to distant observers, meaning that seconds on the star pass more slowly than on Earth. Neutron stars also rotate incredibly fast because they conserve angular momentum as they shrink. Some spin hundreds of times per second, emitting beams of radiation from their magnetic poles. These spinning neutron stars are called pulsars, and their radiation sweeps across space like cosmic lighthouses, which astronomers can detect as precise pulses of radio or X-ray signals. Adding to the extremes, many neutron stars have magnetic fields trillions of times stronger than Earth's, capable of stripping electrons from atoms at a distance and twisting surrounding plasma into complex structures, a type of hot, charged gas that behaves differently under such intense forces. The outer layer, called the crust, is solid and incredibly rigid, possibly a billion times stronger than steel, while the inner core is still mysterious, potentially containing superfluid neutrons, exotic particles like hyperons, or even quark matter, a state where protons and neutrons break down into their most fundamental components. Neutron stars are not just incredibly dense and heavy, they are cosmic laboratories where nature tests the limits of physics, from nuclear forces to general relativity and quantum mechanics. Their formation in violent supernovae, their mind-bending density, their extreme gravity, rapid rotation, intense magnetic fields, and mysterious inner cores make them some of the most fascinating objects in the universe. Studying them allows scientists to explore the behavior of matter under conditions impossible to reproduce on Earth, giving us a glimpse into the universe's most extreme environments, and a doorway into understanding how the laws of physics operate when pushed beyond anything we experience in daily life. A neutron star is far from uniform. It is an incredibly complex object with distinct layers, each more extreme than the last. The crust, which forms the outermost layer, is only a few hundred meters thick, yet it is unimaginably dense and strong. It consists of a lattice of atomic nuclei immersed in a sea of free electrons, creating a structure that is possibly 1,000,000 times stronger than steel, making it the hardest material in the known universe. Beneath the crust lies the outer core, where neutrons dominate the composition, along with a small fraction of protons and electrons. Here, nuclear matter is packed so densely that a single teaspoon would outweigh Mount Everest by billions of times, and the pressure is far beyond what can be recreated in any laboratory on Earth. At this depth, matter behaves in ways that challenge our understanding of physics, exhibiting properties like neutron degeneracy pressure, a quantum mechanical effect that arises because neutrons resist being squeezed into the same state, a force that actually prevents the star from collapsing further into a black hole. And then there is the inner core, the most mysterious and least understood region. Scientists have many theories about what exists here, but no one knows for sure. It could be a superfluid of neutrons, a frictionless fluid that flows endlessly without losing energy. Some theories suggest the presence of hyperons, particles containing strange quarks that normally do not appear in ordinary matter, or even quark matter, a hypothetical state where neutrons and protons dissolve into their fundamental building blocks, quarks. There is also speculation about strange stars where strange quark matter dominates, potentially forming an ultra-stable type of matter that could, in theory, convert normal matter into strange matter if contact occurred. Conditions in the inner core are so extreme that, well, our current physics can only provide educated guesses, making it one of the most enigmatic environments in the entire universe. From the rigid, metallic-like crust to the bizarre, possibly exotic matter in the inner core, neutron stars are layered worlds of extreme physics, each level unlocking new mysteries about the behavior of matter under pressures, densities, and magnetic fields beyond anything we can experience on Earth. The inner core of a neutron star remains the ultimate cosmic mystery, a place so extreme that even the most advanced physics on Earth can only offer theories about what might exist there. One possibility is the presence of superfluid neutrons. A superfluid is a state of matter in which particles flow without friction, meaning the neutrons could move endlessly within the core without losing energy. This is completely unlike anything we experience in our daily lives on Earth and represents one of the most bizarre forms of matter known to science. Beyond superfluids, the extreme pressures in the core, millions of times stronger than anything we can create in laboratories, might allow the formation of exotic particles. These could include hyperons, particles that contain strange quarks, which do not normally appear in the matter we encounter around us, or even free quarks themselves, the fundamental building blocks of protons and neutrons. Going even deeper, some theories propose the existence of quark-gluon plasma at the very center. In this state, matter breaks down entirely into its most fundamental components, quarks and the gluons that bind them together. This plasma would be billions of times hotter and denser than the core of the Sun, a searing, ultra-dense soup of subatomic particles where the normal rules of matter no longer apply. Another fascinating possibility is the formation of a strange matter core, which could make the neutron star a so-called strange star. Strange matter is theoretically ultra-stable, and in a hypothetical scenario, if it came into contact with ordinary matter, it might even convert it into strange matter, spreading its exotic properties. In other words, the inner core of a neutron star could be one of the most exotic and extreme environments in the entire universe, containing matter that behaves in ways our minds can barely imagine. From frictionless superfluids to hyperons, free quarks, quark-gluon plasma, and potentially strange matter, the inner core pushes the laws of physics to their absolute limits, giving scientists a tantalizing glimpse into the behavior of matter under conditions impossible to replicate on Earth. Studying these cosmic enigmas not only helps us understand neutron stars themselves, but also opens a window into the very nature of the universe, challenging our understanding of matter, energy, and the fundamental forces that govern everything around us. But how do scientists study something that is invisible and millions of light years away? Neutron stars are so distant and extreme that we cannot physically probe their surfaces, let alone their mysterious inner cores. Yet, astronomers have developed clever methods to uncover their secrets. One of the most revolutionary tools is the observation of gravitational waves. These are ripples in the very fabric of space-time, first predicted by Einstein, which are generated when two massive objects, like neutron stars, spiral into each other and collide. By carefully analyzing these ripples, scientists can learn about the density, composition, and even the deformability of neutron stars, offering indirect clues about their internal structure. Another key method is X-ray observations. The NICER telescope aboard the International Space Station focuses on X-rays emitted from the hot surfaces of neutron stars. Tiny fluctuations in these X-ray emissions as the star rotates allow researchers to estimate the star's size, mass, and density with astonishing precision. This, in turn, constrains models of what the star's interior might look like. Additionally, astronomers study pulsars, which are neutron stars spinning at incredible speeds, sometimes hundreds of times per second. These pulsars emit beams of radiation from their magnetic poles, sweeping across space like cosmic lighthouses. By measuring the precise timing of these pulses, scientists can infer not only the star's rotation rate and magnetic field strength, but also aspects of its internal composition and structure. For example, tiny irregularities in the pulse timing can hint at phenomena like starquakes or changes in the superfluid core. Even with all these advanced techniques, the inner core remains largely theoretical. We can model it using physics and simulations, but we cannot see or touch it directly. Each new observation adds pieces to the puzzle, yet nature still has the power to surprise us, revealing exotic states of matter and behaviors that challenge our deepest understanding of physics. Studying neutron stars is like peering into a cosmic laboratory where the universe itself pushes matter to extremes far beyond anything we can reproduce on Earth, giving us a glimpse into the most mysterious corners of reality. The core of a neutron star is far more than just incredibly dense matter. It is a gateway into the extremes of physics, a natural laboratory where the laws of nature are pushed to their absolute limits. Inside this tiny city-sized object, matter exists in forms that we cannot reproduce on Earth. Neutrons may flow as superfluids, frictionless and endlessly moving, defying our everyday experience of how fluids behave. Exotic particles such as hyperons, particles containing strange quarks, could emerge, while deeper still, neutrons and protons might break down into their fundamental building blocks, forming quark matter, a state so extreme that it challenges the very foundations of particle physics. Some theories even suggest the presence of strange matter, a hypothetical, ultra-stable form of matter that could, in principle, convert ordinary matter into its exotic state. These possibilities are not science fiction. They are the very frontier of human understanding, pushing physics into realms that are still largely unexplored. So, the next time you gaze at the night sky, remember that among the billions of stars scattered across the cosmos, some tiny, rapidly spinning points of light hide cores of unimaginable density and mystery. In those tiny objects lie conditions that could rewrite everything we know about matter, energy, and the fundamental forces of the universe. They are cosmic laboratories, teaching us about extremes that stretch our imagination, and reminding us that even in the vast, silent night of space, nature holds secrets far stranger and more fascinating than anything we have ever experienced on Earth. The heart of a neutron star is not just a core, it is a window into the ultimate mysteries of the universe, waiting for us to uncover its secrets.